In this video, I'll help you solve the ALEKS problem called predicting the products of a gas-evolving double displacement reaction. To help you solve this problem, you're probably going to want to have access to a table of polyatomic ions. I recommend the table from the website socratic.org. You may also want to have access to a periodic table. Now, in a double displacement reaction, the cations of the two reactants trade places with each other. So the first thing that we should do in the process of trying to predict the products of this reaction, the first thing that we should do for each one of these reactants is figure out what the formula of the cation and anion is in each reactant. So basically what we're going to do is split these reactants up into their respective cations and anions. Now this is the part where it can get a little bit tricky when you're looking at an equation, a formula for an ionic compound. If you can see a total of 3 different types of atoms, which is what I have here, potassium, carbon, and oxygen, that means that you have a polyatomic ion present somewhere in this compound, and that's where this table of polyatomic ions is really going to come in handy. In the polyatomic ion, the atoms of the polyatomic ions stay together. So by that, I mean that either these two atoms, K2C, make up the polyatomic ion, or these two atoms, CO3, make up the polyatomic ion. The polyatomic ion is never going to be two atoms that are separated by something else in the middle of the compound. So this table of polyatomic ions, one of the reasons I really like it is because not only does it have the ions alphabetized by name, but it also has them alphabetized by element. And so we can look on the table of polyatomic ions for K2C, and we're going to see that it does not exist. We can look for CO3, and we can find it right there. So that is for this K2CO3, that is our anion, and we're just going to write that down including the charge. And then that means that this potassium is our cation. Now, be careful, our cation is not K2. That would be a polyatomic ion. If K2 was a thing, we'd be able to find it somewhere on this chart. So that this compound is not a K2, does not contain a K2 ion, rather it contains 2 potassium ions. We need to know what their charges are. That's where the periodic table is going to come in handy. It's helpful if you can remember that all of the elements in the first row on the periodic table, or the first column on the periodic table, they all form +1 ions. Potassium is located in that first column, so it is a +1 ion. And just to finish filling this out, column number 2 are the +2 ions, 3A are the +3 ions. These guys tend to not ionize, and then we count down with our anions, negative charges. So this helps us remember the charges on ions that are not polyatomic. So there is our first compound split up into cation and anion. Now we're going to do the same thing for our second compound. We're going to split this up into cations and anions. Now again, we can see a total of 3 different types of atoms, which means there's a polyatomic ion present. That polyatomic ion is either HN, you could look for it on the table, or the other option is NO3, and that is one that we're going to find, NO3, right there. So our anion for this compound is NO3, that's a -1 charge, and then that means that our cation is the hydrogen ion, which is also located in the column of +1 ions. So there we go. Now, once you get your reactants split up into their respective cations and anions, your next job is just to remember what's going on in a double displacement reaction. In the double displacement, as I had mentioned in the beginning of the video, the cations are simply trading places. So instead of the potassium ion being connected to the carbonate anion, which is what we have in the reactant, the potassium ion is going to link up with the nitrate anion, NO3-. Now this 2 that I wrote in front here, I'm going to get rid of it for a minute. Actually, I'm going to get rid of it forever because we may not necessarily need 2 of those potassiums in this formula. So our potassium ion we know is going to be connecting with the nitrate, and see if I get a different color here, our H+ ion is now going to be connecting with the CO3. And again, this is double displacement where the cations just swap which anion they are bonded to. So the H+ is not anymore going to be bonded to the NO3, the H+ is bonding to the other anion. Now what we're going to do is write the formulas for these new compounds. We have the K plus ion and the NO3 minus ion. To charge balance them, we have a +1 charge and a -1 charge. That means that they're going to come together in a 1-to-1 ratio. KNO3, we just need one of each. Alex does want us to have the states on these. I'm going to come back and fill in the states in a minute. Right now, I'm just worried about getting the formulas correct. The other thing that we're going to make here is formed between the H plus ion and the CO3 2 minus ion. Because the carbonate is a 2 minus charge and the hydrogen is only a +1 charge, we're going to need 2 of these H plus ions to balance out the -2 charge of that carbonate. So that is going to be an H2CO3. Now, before we continue on in this, we've got a few more things to do. We do need to go through and make sure that the equation is balanced. We also need to go through and add states to our products. However, Alex has thrown a pretty major curveball with this particular problem in that some of the reactions, some of the problems that you're going to get, some of the reactions are going to produce products such as H2CO3, which are not stable. They actually don't exist in these reactions. So if you end up producing a product of H2CO3, like I did in my reaction, that is actually going to immediately decompose and turn into water, which will be in the liquid phase, and CO2, which will be in the gas phase. And that is just something that Alex just expects you to know when you're solving this problem. So if you make H2CO3, you're actually going to not write that as the product of this reaction. Instead, you are going to write H2O, and that is in the liquid phase, and you're going to write CO2, and that is in the gas phase. Now this reaction is not the only one that produces a wild card, H2CO3. Some of the reactions that I looked at produce the product H2SO3, and that molecule is also unstable and decomposes immediately to SO2 gas and H2O liquid. Now, fortunately, when I was looking through the ALEKS problems, the different options for this problem, those were the only 2 weird molecules that I saw. So those are really the only 2 that you need to look out for. I did see some reactions that produced H2S as a product, and that's fine. That's stable. It doesn't need to be rewritten as anything else. But I just wanted to let you know, if you do make H2S as a product, that substance is going to be a gas. Okay, so I think those are all the wild cards that Alex has for this problem. Now that we have all of our products, and we've got the states predicted for these 2, the state of the other compound, so the other thing that you make, that is always going to be aqueous. For all of the versions that of this problem that I saw, the products were either included H2O liquid with CO2 gas, SO2 gas with H2O liquid, or H2S gas, along with one other thing that was going to be aqueous. And we're not quite done yet because we do have to make sure that the equation is balanced. It is not balanced because I have 2 potassiums right here, and that means that I need to have a 2 in front of this KNO3. When I put a 2 here, now I'm going to have 2 nitrogens, which means I'm going to need to have a 2 in front of this HNO3 molecule, and that should take care of it. These, in general, these usually aren't that tricky to balance, even though they look like they could be. 2 potassiums, 1 carbon, 1 carbon, 1, 2, 3, 4, 5, 6, 7, 8, 9 oxygens, 1, 2, 3, 4, 5, 6, 7, 8, 9 oxygens, 2 hydrogens, 1 nitrogen. Looks good.